All right, welcome back. We are having a quiz, as I mentioned on our announcement page last night, coming up this Thursday. That's on March 26th, but that will not be on Chapter 7, which I'm going to lecture on now. However, the outer planets, the subject of Chapter 7 in your textbook, will be on our midterm. That's coming up on the Wednesday after we return from spring break. That's 4:15. And remember that your homework is due at that time. So you can double check the announcements page for the formatting on that I would like, if possible, for you to get that into a Word format, and that will make it much easier for me to handle with my new system. Okay, so how do the outer planets differ from the inner planets? Well, the outer planets, and let's just look up at the data projector for a second. Outer planets are big, much bigger than the inner planets in terms of volume, but they are much lighter in terms of composition. They're made of light gases like hydrogen and helium, and they're much farther apart from each other. So we compare Jupiter, for example, to the Earth. You could fit more than 1,000 Earths into Jupiter. And Saturn, the next biggest planet in the solar system after Jupiter, you could fit maybe about 800 Earths into Saturn. Uranus and Neptune, more like maybe 64 Earths into Uranus or Neptune. And so they're much bigger. They're made of lighter materials. Just hydrogen and helium, mostly. And they have a composition that's more like the sun than like an inner planet. These outer planets are far apart from each other relative to the inner planets. And none of them have solid surfaces, so you couldn't land a rocket ship on any of these outer planets. Now, this is not true for the moons of these outer planets, but it is true for the planets themselves. The reason for this is their very gaseous composition of hydrogen and helium. This makes for a surface, for example, for Jupiter, in which if you were falling through the atmosphere of Jupiter, this would be the interior of Jupiter here. As you fall through, you get to this point, it might be 50% gas, 50% liquid. So there's no well-defined surface. And even though we do have liquid hydrogen in the interior, and also liquid helium in the interior, up here it's pure gas, but then as you start falling through, you don't have a splashdown point at which it suddenly turns into a liquid. But rather you fall through thousands of kilometers of distance, and then finally here you might be 90% liquid and 10% gas. And then eventually Jupiter may have a solid core. In the deep center of Jupiter, we're not sure about this, but we think that this is true, that Jupiter has a solid core. So eventually then you would get to a point where, yeah, it's pretty much liquid hydrogen and helium in the interior, But then finally, if you continued to be compressed down and you could survive that, which you wouldn't be able to do, but if you could survive it, you would eventually encounter what we probably think is a solid core. And this might be more like an inner planet in composition with rocks and metals. So this is the conventional thinking, at least, is that the outer planets have this huge amount of gas which has been compressed down into a liquid, but then in the center we may in fact have a solid core. So in terms of Jupiter and Saturn, we usually like to talk about those planets together because of their similarities. For Jupiter, its distance from the Sun is about 5 astronomical units. Remember that an AU is equal to the distance from the Earth to the Sun. For Saturn, it's about 10 AU. The radius for Jupiter is something like 11 times the radius of the Earth. For Saturn, it's about 9 times the radius of the Earth, where RE here is the radius of the Earth. The period of orbit around the Sun for Jupiter is about 12 Earth years, and for Saturn it's about 29 Earth years. And the atmosphere for both of them is a series of oppositely directed wind currents called zones and belts. And so these winds travel at hundreds of miles per hour in opposite directions. So create a very turbulent environment on the surface. So we see this kind of a banded structure then for Jupiter, in which the rotation rate is very fast. And here we'd have a zone, and then we'd have a belt. Zone, belt, zone, belt, zone, belt. So these zones and belts are oppositely directed wind currents. So we might be on the order of hundreds of miles an hour, maybe 200 miles per hour in that direction, and then in the opposite direction, 200 miles per hour on the adjacent region of the atmosphere. And then we also have cyclones. So these cyclones then are places where we have vortexes of wind and they can be stable for hundreds of years. Whereas a cyclone on the Earth may dissipate in a few days. What we call the Great Red Spot on Jupiter has been stable, we think, for at least 400 years. And maybe even longer. This is just as long as we've been measuring. Galileo was able to see the Great Red Spot. But we don't know. It could have been going on for 1 million years before Galileo. We can't be sure. With the fact that the Great Red Spot is starting to dissipate now, gives us an idea that it maybe is a more temporary structure than that. But we can't be sure that that's just, it could be just a normal variation. in the atmosphere. So let's pan up to our look at the data projector, and we can see that picture of Jupiter, and we can see that it's a very banded structure with the zones and the belts, as I indicated, being intense regions of winds that are moving in opposite directions. So we might wonder then, well, you could kind of explain maybe why you would get wind currents going in one direction if that were the same direction as the rotation of the planet. But how do you get them going in opposite directions? Well, we think that it has to do with heat that's released from the interior. So here we see these zones and belts a little closer up. See up here in the upper left, there's a little vortex that looks a lot like a cyclone. And then here's another little one. Notice that these kind of vortex structures seem to form right at the junction between the zones and the belts. And here's the great red spot. The great red spot is a giant cyclone that, as I mentioned, has been around since the time of Galileo, almost 400 years ago. And this thing is, you could put 3 Earths into this. And so that's how big that cyclone is. We'll notice there's some other cyclones here too. What about Saturn? It's got them too. And so how do we explain these things? Well, we think that they're stable because they are at the border between a zone and a belt. So here we would have, say, a zone. Here we'd have a belt. And so this kind of a swirling action then could give rise to a vortex. So we don't have things like this on the Earth, and so this is the reason why our cyclones don't last as long, we think, on the Earth as they do on Jupiter and Saturn. Another thing that we can mention about Jupiter and Saturn is they have a rapid rotation rate. Even faster than the Earth's. For Jupiter and Saturn, it's about 10 hours for both. So if you were trying to view Jupiter or Saturn through a telescope and you had all night to spend watching, say, Jupiter, and it was visible for the entire evening at your location, you would be able to see both sides of Jupiter, and so you would be guaranteed of being able to see the great red spot. In just one night's worth of viewing, you could see all of the points of interest on either Jupiter or Saturn because of their very rapid rotation rate. Of course, with Saturn, Saturn is out twice as far away as Jupiter. So if you were to go to Jupiter, you're only halfway to Saturn. And so Saturn is not going to be as visible for two reasons. One is that it's farther away, and two, it's not quite as big. And so there's less reflected radiation coming out from the sun, and the sun's radiation follows an inverse square law both ways. So not only is there less light hitting Saturn, then the light spreads out more on its way back to us here on the Earth. And so these are the basic points then that you'll see in those videos that I recommended that you view. And so I just wanted to try to tie that together here with some of the things that I thought were important regarding Jupiter and Saturn. But we still have to look at the moons. So that's another video that I hope that you'll look at if you haven't already looked at it. The moons of Jupiter and Saturn are extremely interesting. Now, how many moons does Jupiter have? Well, it's constantly changing. It's actually the same number, pretty much, but we're discovering more all the time. And so somebody asked me a while ago, how many moons did Jupiter have? I said something like, I don't know, 65 or something. It had already gotten up into the 70s or 80s by then. And so you have to stay on top of it because they're constantly discovering more. But there are 4 main moons of Jupiter. These are the really big ones. So here's Jupiter. And then we've got Io, Europa, Callisto, or Ganymede, and then Callisto. Now, the kinds of questions that I might ask you on an exam would be ones perhaps where you would match things up. So there might be some that's incredible thing about one of these moons that would be just more spectacular than any of the other things, and you would have enough familiarity, hopefully, to be able to identify which thing matched up with which. For Io, this is about the size of our moon. And this is true for both Io and Europa. They're about the size of our moon on the Earth, which means they're about 1/4 the diameter of the Earth, both of them. But Io is remembered for being highly volcanic. You may recall we talked about tidal forces and how they work, the effects of the sun on the Earth and the moon on the Earth, and then the effect of the Earth on the moon as well, distorting the moon's shape, the effect of the sun and the moon on the Earth affecting the Earth's tides. Well, here, Jupiter is pulling so hard on Io that all 4 of these moons, as a matter of fact, keep their same faces pointed toward Jupiter. Just the same way as our moon keeps its same face pointed toward the Earth. So they all keep their same face pointed toward Jupiter, but Io is the most distorted, and Io also gets extra kicks from Europa. As Europa goes by, that gives it a little stretch in the opposite direction. And so Io then is the most volcanic. As a matter of fact, it's the most volcanic object in the solar system. And you'll see this in the video on Jupiter's moons. Let me just show you a couple of pictures on the data projector that also illustrate this. There's Io and Europa relative to the size of Jupiter, so you can see how much smaller they are, even though they're the size of Earth's moon. They're just these little dwarfs in comparison. And then you also have a nice scale comparison there for the size of the Great Red Spot. But here we have a nice picture of Io. And you'll notice here in the top, we've got a volcano that's shooting up hundreds of miles into the atmosphere of Io. And so this is a moon that's literally turned itself inside out over geologic time. So in other words, the outside has become the inside, and everything that's on the inside has become the outside at one point, so that it's completely recycled itself due to intense volcanic activity that's driven by the heat from the tidal forces exerted by Jupiter and Europa. So we can say then that these volcanic eruptions on Io are caused by strong tidal forces. As a matter of fact, you could get temperatures on Io near a volcano that could be close to 1,000 degrees Fahrenheit, but then nearby in a cooler region, it could be 300 below. And so these lava flows would move faster than you could run, but you might be able to outrun them on a dirt bike. So you can imagine pedaling as hard as you could, and the backside of your body is starting to heat up to nearly 1,000 degrees, whereas the front side would be at hundreds of degrees below zero. And so that's the kind of radical environment that exists on Io. Now, Io has many lava tubes and very strange places where we might be able to hide out and actually investigate the structure of Jupiter. But Jupiter produces so much radiation that you would be killed in less than 1 second. You would get a lethal dose of radiation if you flew close to the surface of Jupiter without some kind of a protective radiation shield. Okay, and so Io then, highly volcanic. What about Europa? Well, Europa, we think, has a deep water ocean with a thick ice crust. And some people believe that the ocean of water on Europa may have a volume that's more than 3 times the volume of all of Earth's oceans. So why is there water there and no water on Io? And why is it water if it's hundreds of degrees below zero? So we've got this thick ice crust, then a deep water ocean, and then we think rocks, and mostly rocky material toward the center. This is for Europa. So why do we get a deep water ocean if it's 300 degrees below zero? You'd think the water would freeze. Well, the reason for this is that there's also tidal action, and that tidal action produces underwater volcanoes. So Europa is also being affected by tidal forces, but not enough to evaporate all the water, but just enough to keep the water in a liquid state. Okay? And so whereas Io evaporated all of its water long ago, Europa still has a great supply. And that may also be the case for Ganymede and Callisto, but we think that Europa has more water than any of the other moons. And so an interesting thing that we'll be able to explore in the future then is the possibility for life in this deep water ocean or somewhere else in the outer solar system where there's a source of heat and there's also liquid water. If you have the raw materials for life and you have a source of energy, you have water, then a lot of people believe that that is enough to ensure that some form of life will develop. Of course, we can't be sure of that until we found life in some location that is other than the Earth. We've failed to find it anywhere else, but the results are suggestive of the fact that life may be all over the place, but probably mostly just primitive forms of life. As we saw in the ET lecture before, the chances of advanced extraterrestrial life existing on a given planet, probably very small. But single-celled creatures and simpler forms of life might be almost everywhere.